everyone. Welcome to the another session of digital signal processing. In the last session, we had started discussion of FIR filter design. We had discussed various window function, and one of the popular window function was left for the discussion. That was the Kaiser window. So we'll be discussing the Kaiser window design in detail in today's session. So this Kaiser window is a practical filter design which is used basically for designing of the finite impulse response filter like other windows like Hamming, Hanning, Bartlett that we had previously discussed, but it has the quality that it gives me the flexibility to obtain certain kind of response which is said to be more practical. So this is based upon the empirical formulae which has been tried and tested over the years, generating acceptable performance for this particular design. So J.F. Kaiser developed this practical procedure for the design of the FIR filter, which uses certain kind of empirical formulas, kind of the windows that we had discussed previously, like of the Hamming window, Hanning, Bartlett and Blackman windows. They were also having certain formulas which were fixed, having a fixed nature. For example, if we talk about this particular Hanning window, the coefficient that we were defining in that window was fixed, like 0.5 minus 0.5, and the basic function that we were using was a cosine function whose range was varying depending upon the length of the filter that we are going to design. Similarly, for the other window, Hamming window, the coefficient were fixed. So this cosine was the main function which was used for windowing or truncation of that infinite series to which I want to make finite. Here this is the multiplicative factor and this is the factor which is either added or subtracted from this particular truncation window. But when we start designing of a filter using this Kaiser window, these limitation of having these constant coefficient or fixed value of coefficient is eliminated. I can change the slope of the window. I may use certain kind of another kind of window function which cannot be specifically a cosine function. So that's why I call that I get more kind of flexibility in designing of the filter using this Kaiser method. So in this design make use of the practical filter response characteristic, and window known as is called as the Kaiser window. So more or less the design procedure would appear like we are designing some IIR filter. Some specifications of low pass filter would be given. We start calculating the order of the filter. So more or less it appears like designing in the analog domain like we do with the IIR filter, but we are basically designing the finite impulse response. So these formulae that we'll be seeing which are used in this Kaiser window, they are empirical in nature and they are depending upon the trial and error procedure which has been done and performed previously in the laboratory, and it is based upon the experience which is suiting the requirement of particular application for which we are designing the FIR filter. So what we see that using this empirical formula for the designing, we find that the filter that are constructing using this Kaiser's design, this is giving me the excellent result. So if we compare all other windows with the Kaiser window, the Kaiser window would be considered as the best form of designing for FIR responses. So as we saw that it is going to use, like we say here, it is basically using certain characteristics, the practical filter response characteristics for designing. So here I can design, I am seeing here the response of a low pass filter, and whatever characteristic possible, I would be talking about those characteristics. So these all deviations, as we had discussed in the IIR filter, they're called as my passband ripples. I must know their value. Similarly, ripples in the stop band, these are stop band attenuation values. In between these two edges, I have this transition band, and this transition band, the width of this transition band is calculated as the difference between these two frequencies. So this omega 1 frequency is my pass band edge frequency, and similarly this omega 2 is my stop band edge frequency, defining my transition band. So if I need to calculate this difference between these two edges, I simply need to subtract these two frequency, and I call that or represent that transition band with another parameter which is called as delta omega. If I need to talk about the cutoff frequency omega c, I may take average of these two frequencies as omega 1 plus omega 2 divided by 2. So these two parameters would come from the given graph. Different values have been specified. If two cutoff frequencies have been or edge frequencies have been defined, I can calculate the transition band. I can calculate this cutoff frequency, which is average of the given two frequencies. So from the pass band edge, that is omega 1, stop band edge or attenuation edge, that is omega 2, I am calculating the bandwidth of the transition band, that is difference between two frequencies. Similarly, the cutoff frequency can be calculated, which is the average of the frequencies omega 1 and omega 2. So from the given specification, we can calculate these two important parameters, which is the width of the transition band and cutoff frequency. Then we can move with the designing of the Kaiser window. We'll see certain specification, and according to these specification, we'll try to design the Kaiser window function. So what specifications have been given? First of all, again the specification for the low pass filter have been given. First frequency is pass band end frequency, that we have denoted as omega 1. Gain in the pass band has been given. Frequency from which stop band is beginning, omega 2 has been specified. Gain, or you can say attenuation in the stop band, has been given, and sampling frequency has been given. So sampling frequency, the role of sampling frequency is only the normalization of these given frequencies. So to begin with the designing of the Kaiser window, what I see, first step, because sampling frequency is given, I would normalize these frequencies. So first frequency is 400 Hz, second frequency is 800 Hz. So I would divide these frequencies with 2000. This Hertz has to be converted into radians per second. That means the frequency has to be converted into omega. I'll multiply it with 2 pi. So these are normalized frequencies, omega 1 and omega 2, which comes out to be 0.4 and 0.8. From these normalized frequency, I can calculate two parameters which are desired. First parameter is the cutoff frequency, another parameter is the width of the transition band. So cutoff frequency can be taken as average of these two values, 0.4 pi plus 0.8 pi by 2, and transition width would be difference of these two frequency, 0.8 minus 0.4, 0.4 pi. Now, second thing which has been given is gain in the pass band and gain in the stop band. So I would define this H1, the transfer function, as 20 log 1 plus delta 1, 1 minus delta 1. From here, I would calculate the value of different parameters, delta 1 and delta 2, which is attenuation in the pass band and attenuation in the stop band. So H1 and H2 are something that are the transfer function of the low pass filter. And whatever value I get of these two attenuation, I need to choose the minimum of two values. If this is coming as say 0.05, this is coming say 2, I would choose this particular value of delta 1. And this is particular corresponding values that I can calculate using the given values, that 10 H1 by 20, 10 H1 by 20 plus 1 and minus 1. H1 is given here as 3 dB, minus 3 dB because this is attenuation, and minus 25 dB. So substituting H1 here, substituting H2 here, I would calculate my parameters delta 1 and delta 2. Once these two values have been calculated, I would take minimum of 2. So delta 1 is 0.171, delta 2 is 0.0562. So minimum of these two is second one. So for my further calculation, I'll be talking about or working with this minimum value, that is 0.05623. So the next thing is, once I have calculated my delta, I have to calculate the modified response of this stop band, or whatever I have depicted it over here. H2 delta 2 is 10 raised to the power minus H2m, or I can say this is my H2, which is depending upon delta 2. Now delta is 0.056. So I can calculate modified value of this H2. So H2M is modified value of H2 at new value of delta which is minimum of 2 delta values that we have just calculated. This modified H2M would be required in further calculation in the order of that particular filter. So once H2M has been calculated, I need to calculate the parameter that is alpha. Now this alpha is actually something which is important in Kaiser window because this is responsible for giving me the desired slope of the frequency response. So here also we have defined some empirical formulas by which we have to choose the value of alpha. Alpha can be 0.1102 multiplied by this bracket which contains H2M minus 8.7. It can be 0.5842 H2M minus 21 raised to the power 0.4 plus 0.07886 H2M minus 21. And third value can be 0. Now how to decide out of these three equations or these three values of alpha, which value should I choose? So this choice would depend upon the value of H2M which I have just calculated. If this calculated value of H2M is greater than 50, I would choose upon this first equation, and from here substituting the value of H2M, I'll calculate the value of alpha. Second, if this H2M, the value of this H2M lies between 21 and 50, the second equation would be used to calculate the value of alpha. So here and here, I would substitute this calculated value of H2M and calculate the value of alpha. If the value of H2M comes out to be less than 20, then simply I would say that alpha is equal to 0. So that's why calculation of this parameter H2M is important, because from this only I am calculating my Kaiser window parameter alpha. So here I can see that this particular modified value of H2M comes out to be 25 dB. 25 dB is lying in the second range. So this equation is being used for the calculation of alpha. So once I substitute the value of H2M, I get the value of alpha which comes out to be 1.33. Once I have calculated H2M, I have calculated alpha. Now I need to calculate the value of N, which is the important value. That is the filter I am designing, its order has to be calculated. So first of all, this parameter M would be calculated and order would simply come from this particular value. If I multiply M by 2, it is equal to the order of that particular filter. So this M has another empirical representation, that is H2M minus 7.95 divided by 2.285 multiplied by delta omega. So what is delta omega? In the starting of this numerical, we had calculated the width of the transition band, and width of transition band was depending upon two cutoff frequencies, omega 1 minus omega 2. So initially we have calculated this delta omega. I need to substitute this delta omega. I need to substitute the value of H2M and I can calculate M. So here in this I am getting M as 6. So from this M I can directly calculate N by multiplying it with 2. So N comes out to be 12. From N I can calculate the length of the filter, which is nothing but N plus 1. So the length of the filter that I am going to design using this Kaiser procedure would be 13. Next is the Kaiser function. Once I have calculated all the parameters, I need to define the Kaiser window. Now anything in this function which is I naught is a function of alpha, square root of 1 minus n over m square, overall division by 1 naught alpha. So I can see there is no constant value. All these factors of this Kaiser window which I can see in this formula, they are alpha. which I calculate depending upon H to M, N, the length of the filter, M. So depending upon if I change the value of these parameter, this Kaiser window, the response of this Kaiser window can be changed. So I do not have a window which has a fixed response like Hamming, Hanning or Blackman window. I am designing a window according to my wish, what kind of response do I desire. By changing the value of these coefficient, I can change the response of the Kaiser window. So what this I naught is showing me? I naught is a function of some parameter, say x. This I naught x is a mathematical's most popular Bessel function. So whatever value of this x I calculate, x is actually showing me alpha under root of 1 minus n over m whole square, and in denominator I naught is the function of direct alpha. So this particular coefficient has to be calculated. It would come some numeral value, maybe in decimals, maybe an integer value, and depending upon that integer value, I would calculate, say first is beta, this function I am representing as beta, in denominator I have alpha. So all those Bessel's function have their certain values at beta and at alpha. So we have a Bessel function table. This is a Bessel function table, a section of Bessel function table, which we are using here for only the example, in which I can see there is a column and there is a row which have a different values. In column we have integers value ranging from 0 to n, and in this particular row it is a value ranging from 0 to 0.1, 0.2 till 0.9, and this is my multiplier factor. So using this table, if I am getting certain value of, say, numerator, if I am talking about I naught, say this is my beta, this is my alpha, it comes out to be certain value, say it is a function of some value 1.33, and denominator is the function of some value, say 1.54. So this 1.33 and 1.54 have to be used here from this table. Wherever they coincide, a continuous value would be picked up, 1 with 0.5. So combination of these rows and column would give me the value of one Bessel function, either I of 1.33 or I of 1.54. I would simply pick up these values from the table with certain multiplier. It is 1, so no significance. So in the lower values it can be 10, 10 raised to the power 2 or 10 raised to the power 3. So in this way I would pick up the value of Bessel functions from this Bessel table. So here I can see in the numerical, this I naught is a function of particular value 1.31 and 1.33. The Bessel function table gives me the value of 1.31 as 1.4773, and for 1.33 this Bessel function is 1.496. So this window gives me the very first sample for n is equal to 1, because length is m, length was n plus 1, that was 12 plus 1, 13. So this n would range from 0 to m minus 1. That means it would 0, 1 and a maximum value would be 12. So for all the values of n, I would try to calculate the samples of window function, substituting the value of Bessel function. So both the values of this Bessel function would be divided, and I get the first sample value of my Kaiser window, which is coming out to be 0.9. Similarly, I would keep on changing the value of n. New values of Bessel function would be taken from the table and all other samples would be calculated. So this is how I get a practical formula whose response can be modified by changing the value of the input parameters. So in this way, I get all the samples of the Kaiser window. So once I have got all the samples of the Kaiser window, what I have to do, I have been given certain function, say h omega as e raised to the power minus 2j omega with certain limit, say from minus pi by 4 to pi by 4 and 0 otherwise. So how to calculate the response, finite response for this particular infinite response that I get? The procedure would remain same that we have used for Hamming-Henning window for designing of the finite response. So what we were doing that from h omega, I was generating hn by taking inverse transform, inverse Fourier transform. From this h, substituting the value of n from 0 to m minus 1, I was calculating all the samples h0, h1 and so on. Then I was talking about the window function, was calculating all the parameters of window function ranging from 0 to m minus 1. And finally, a new truncated response was generated by multiplying all the samples of Hn with all the samples of Wn. So what is the difference with the Kaiser window? In this calculation, there is no difference. Only whenever I have designed this Wn using Kaiser response, I already have all the values, that is 0.95, 0.9, 0.84, 0.76. So the way we were designing a finite response in the Henning window or other kind of window, in the similar fashion we would proceed. Once I'll multiply this Hn with the Kaiser window function values, this new Hn would be transformed into new h omega by taking Fourier transform. So this h dash omega would be my finite response. But this finite response would be practical and the desired response, because the window function that we have taken here was the Kaiser window, giving me the best possible excellent result for the response that I designed for the FIR filters. So what are different features of Kaiser window? These are empirical formulae and they would help in obtaining the length of the filter in a simple and straightforward manner, because I have empirical formulas. In empirical formulas, I am substituting value and getting the value of the length of the filter, that was m. It helps to meet the requirement in the given specification and achieve the desired frequency response characteristics. So like any other window, frequency response characteristics are not fixed. Now here the shape of the main lobe and the side lobe can be chosen by choosing appropriate values of alpha and m. This power was not available for me with the other windows. This flexibility is only possible with the Kaiser window, that I can change the value of alpha and m and I can change the response of the window. So this is a window which is giving me the more practical and the excellent result. With this we end up designing of the FIR filters. In the next session we are going to discuss various limitations that we get because we truncate the response. So those kind of limitations comes under finite word length effect in the digital filter. We'll talk about this in the next session. That's all for this session. Thank you.